In physics, relativistic quantum mechanics is any Poincare covariant formulation of quantum mechanics. This theory is applicable to massive particles propagating at all velocities up to those comparable to the speed of light, c, and can accommodate massless particles. The theory has application in high-energy physics, particle physics, and accelerator physics, as well as atomic physics, chemistry, and condensed matter physics. Non-relativistic quantum mechanics refers to the mathematical formulation of quantum mechanics applied in the context of Galilean relativity, more specifically quantizing equations of classical mechanics by replacing dynamical variables by operators. Relativistic quantum mechanics is quantum mechanics applied with special relativity, but not general relativity. Although earlier formulations like the Schrödinger picture and Heisenberg picture were originally formulated in a non-relativistic background, these pictures of quantum mechanics also apply with special relativity. The relativistic formulation is more successful than any original quantum mechanics in some contexts. In particular, the prediction of antimatter electron spin magnetic moments of elementary spin, one-half harmonious, fine structure, and quantum dynamics of charged particles in electromagnetic fields. The key result is Dirac equation, from which these predictions emerge automatically. By contrast, in quantum mechanics, terms have to be introduced artificially into the Hamiltonian operator to achieve agreement with experimental observations, of course. Nevertheless, RQM is only an approximation to a fully self-consistent relativistic theory of known particle interactions, because it does not describe cases where the number of elementary particles changes. For example, in matter creation and annihilation. By yet another theoretical advance, a more accurate theory allows for these occurrences and other predictions and is relativistic quantum field theory, in which particles are interpreted as fields quanta. See article for details. In this article, the equations are written in familiar 3D vector calculus notation and use hats for operators, not necessarily in the literature, and where space and time components can be collected. Tensor index notation is shown also, frequently used in the literature. In addition, Einstein's summation convention is used. SI units are here. Gaussian units and natural units are common alternatives. All equations are in the position representation. For the momentum representation, and the equations have to be Fourier transformed. See position and momentum space.